Welcome everyone to the very first coffee o'clock session of Q&A. So maybe first we'll start about talking what Q&A is. And Q&A is basically a non-profit that is almost for students, by students, with more experienced people involved. And the basic idea is to build a quantum computing community, or like not exactly quantum computing, quantum technology community in India, because quantum can have sensing and all those other applications that people are also extensively working. And the idea is there are definitely a lot of people in India who are interested in quantum and who know about or who believe in the potential of quantum, and but maybe there is not a sort of community where people can actually get together, and Q India aims to provide such a platform. And so we already have like a small community going on, and most of our activities are on Discord. So someone will be posting the registration link in the chat. So if you're interested, please join us there. And the basic aim of this coffee o'clock session is for facilitating more interactions, and basically for sort of experienced people in the field for them to present their work, and for people who are interested in getting to the field to ask these people some questions, have some discussion going on, and also like share experiences, sort of demystify the entire quantum thing, and to actually show that it's not all so spooky. It's like, it's physics, it's math, it is understandable. You just have to put some effort into it. Right. So with that, for our first session, we are super happy to welcome Akash Kundu. He's a doctoral student from IIT Poland, and he will be talking about variational algorithms, and more specifically this variational quantum Eigensolver, or the VQE algorithm, which is sort of the workhorse of quantum chemistry applications. Okay, so with that, Akash, take it away.
So thank you very much for the nice introduction, and hello everyone. I'm going to specifically talk about variational quantum eigensolver, but I'm going to try to give an overview of variational quantum algorithms. And I think that after the presentation, there will be some clearance about why these variational quantum algorithms are important, and why we are trying to approach quantum mechanically, not like classically. So I'm sharing my screen. So yeah. So I hope you can see my screen.
Yep, all good.
Yes. So as Rishi said, that I am a doctoral student at Institute of Theoretical and Applied Informatics, Polish Academy of Sciences, and today I'm going to talk about variational quantum eigensolver. So okay, so this is the overview of the talk which I'm going to give, and I think there is some problem going on because my screen is freezing. Okay. Yeah, now it's fine. Okay. So so this is the overview of the talk which I'm going to give today. So first I'm going to introduce the quantum algorithms, and actually quantum algorithms has some advantage over classical algorithms, and we can explore these advantages through speed, through storage or memory, and through energy. And if we talk about speed explicitly, forget about for current sake of discussion, if you forget about memory and energy, then we can perfectly remember we probably remember the achievement by Google, which is so-called quantum supremacy, where they sampled one of the outputs from a system of 53 qubits. Actually, if we think about quantum system, there are not only real parameters, but there are also complex parameters. And if we explore the surface of the Hilbert space, so-called Hilbert space, which is like space of all the quantum states, and then it increases exponentially. Like if we have 1 qubit, then we have a Hilbert space of dimension 2. Then if we have 2 qubits, then it is 2 square. If we have 3, 2 cube. So it increases like that. So if we have 53 qubits, then you can imagine that the dimension of this space is around 2 to the power 53. And we have like and sampling one of the outputs from 2 to the power 53 dimensional space is like a very tough job to do. But so you can understand that this achievement was a very big achievement by Google. But the problem was that the problem considered by these people from Google, the researchers, were mathematically very abstract. I mean, mathematically abstraction means that they don't have proper physical implications. So we need some algorithm which are efficiently computable in a quantum computer and have some practical implications, like such as Shor's algorithm. But there is also a very big problems with the Shor's algorithm, because if we go to that, if we think about the Shor's algorithm, then it is basically factoring 2 numbers, nothing more, nothing less. So how efficiently we can factor a number into 2 prime numbers? So in classical computers, we can factor a number of 829 bits. And if you want more information, then you can go through this very nice written article. And next, if you focus on quantum computers, then we factored some numbers using 5, 6, 7 superconducting qubits, and those numbers are 15, 21, and 35. But unfortunately, the 35 number, which is corresponding to 7 superconducting qubits, were giving a result like a factoring numbers. Like if you factor 35, what is that? 5 and 7. 7 into 5 is the factorization result, right? So they are giving the right result like 14%. So this is not like a good result, right? Because 14% is like a very bad probability, like not even close to 50%, like half. So we can say that we can right now efficiently factor a number which can be represented by 6 qubits. So what is the problem actually? The problem actually is that if we increase the number of qubits and if we want to implement the Shor's algorithm, then what happens? We need a very big circuit, like a very big quantum circuit with quantum gates. Like I hope you probably know, like X gate, rotating gate, Z gate, control node, control gates. So we need a very high depth and a large number of qubit circuit, which should be fully coherent. That means the state which we are like there shouldn't be any noise, like there shouldn't be any interaction with the environment. So a system like that, and the connectivity between all the qubits should be proper. Like in IBM system, some of the qubits are not connected. So what happens if we apply some gate like control NOT gate, control X gate? Then if the 2 qubits are not connected, then what happens that the control node doesn't work properly. So the output will be bad, right? So this is like one of the big problems which we need to tackle in like next few years. And also the requirement is not fulfilled with the current quantum hardware. That is what I was talking about. And these are the papers where you can find the classical factorization and the quantum one. Now, so what happens? Like we are talking about an ideal situation where we can implement like Shor's algorithm and it will run perfectly and it can decode any number with that speed, like like the polynomial speed which Shor said in his paper. But before that, we need to explore the quantum algorithms, right? So there is a very nice approach which has been introduced in 2014, which is called variation, like hybrid approach. So in this approach, what we will do, we will be dealing with an era which is called NISQ era, that is called noisy intermediate scale quantum computing era. So here it will be intermediate scale. That means we will not deal with less number of qubits or not with a large number of qubits. Maybe we will deal with 15 qubits, 20 qubits, most probably 24 qubits or something like that, 25. But we will be able to deal with these algorithms in a hybridized versions. And in this case, we will not require a large quantum resource. That means the gate can be faulty, and there shouldn't be. There is no necessity of all the qubits should be connected. And to do this, we are introducing a hybridized version of quantum algorithms. And this hybridized version actually has two loops basically. So first is the cost function evaluation. Actually, this cost function encodes the problem which we are going to deal with, and it basically are the series of gates which we are going to discuss in the next few slides. Don't worry. And in the cost minimization, this second step is basically classical step, where we evaluate a function of our requirement of the problem from this cost function evaluation circuit, and we send that particular function to a classical computer like your laptop or your desktop, whatever, and you try to minimize that particular function to find the your expected result. And we used a parameterized quantum circuit and variationally update those parameters. So this is basically the format. So as you can see that there is a classical computer and a quantum computer, and they are both working like synchronizing. Like the quantum computer is like initiating with some specific state rho k, and this k is the dimension of the state, and this can be like 0000 or something like any special choice of your problem. And this is the unitary, which can be consist of 2 qubit gates, 1 qubit gate, and this is a measurement. So in this case, I showed the partial measurement, but this measurement will fully depend upon that what is the problem statement. And after this measurement, you will finally evaluate this function, which is called a cost function, which will depend upon the unitary operations parameter. Like we basically call it ansatz. And ansatz is a German word. Its actually meaning is, in Germany, it's called approach, like approaching to the solution. So this is like that. So this cost function will depend upon this unitary like ansatz parameters, like the angles and this input state. And we are going to, so this is, as you can see, this is just the cost landscape. Like, is it minimized? Is it not minimized? Like, what is the cost function behavior with respect to our parameters of the circuit, this quantum circuit? And then we send this cost function to the classical computer, and this classical computer just does like run some minimization method. And there are some very well-known minimization methods which are called gradient descent method, if you search about them, and Kobla, and there is a very nice method called Powell and Nelder-Mead. I mean, there is a very big list. So you can use any one of the methods of your choice to minimize the parameter. Now, most of the time, minimization means to make the cost function 0. So if you see that the cost function is not 0, then what you can do, you can try to make it 0. So if you want to try to make it 0, you can choose a different set of parameters here once again, and once again evaluate this function, this cost function, and once again do this minimization until and unless you reach the proper minimum value, which is we more technically called a global minima. And if you don't reach the global minima, we call it a local minima. So let's move to the VQE stuff. Like I'm going to discuss specifically variational quantum algorithm. So it has been introduced by these two guys, like not two guys, actually there are many guys. It is in Etel and in 2014. So this structure has a very nice this structure is very adaptive structure. That means the outcome of your circuit or the cost function, if you say like I told you, it will fully depend upon the given gate structure or the gate sequence. And actually this circuit, like all the variational algorithms, doesn't depend upon if there is some error in the gates or not, because just consider that if you have some X gate or Y gate or Z gate, it doesn't matter. And the problem is that the X gate has some problem, like it is not working properly. So if you run the circuit, then what will happen? You will get a bad output because one of the gate is not working, right? So what you will do, you will evaluate the circuit and get the function and minimize it, but you are not getting a result. So what you will think, okay, so in the circuit, one thing I can vary is that the parameters, like the gates. Then what you do, you use a different set of parameters, a different set of gates to minimize, to get a proper value of this particular function. So this is not like you need a perfect set of gates. You just finding a perfect combination of gates which will give you a proper result, and you don't need any error correction, like we need to correct this gate particularly, we need to correct this qubit, because you are only concerned about the gate sequence.
So Akash, Achintya was asking if you could give an example of a cost Hamiltonian or like a cost function.
Okay, okay, that's why I introduced the VQA, and I will go through it. Yeah,
perfect, great, cool, thanks.
So let us, you're most welcome. So let us discuss about the background of VQA. So actually, VQA is like variational quantum algorithm, and it is like if somebody is a physicist here, they heard this word variational, and it comes from variational method in quantum physics, and this is actually variational method, nothing else. And actually, VQ is like variational quantum eigensolver. So eigensolver means that it is particularly focusing on the eigenvalues and eigenvectors of a particular problem or particular Hamiltonian, if you say, like an energy, a system. So in majority of the cases, we focus on the lowest eigenvalue and eigenvector, because if you go like most of the times we use these variational algorithms to in finance problems and maybe in routing problems, like there is a very famous problem which is called TSP, traveling salesman problem. It is like if there are many cities and if there is a salesman who want to go through all the cities, then what is the best route to go through all the cities and come back to the initial city in less amount of time? What is the shortest path? So to evaluate this problem, we need to find like the solution of the problem is actually lies in the ground state of that particular problem. You know, like you can encode any problem to any Hamiltonian. Hamiltonian means like a series of Pauli XYZ gates. You can just create this problem in such a manner, like this city is visited or not, this city is visited or not. Like that, you can put many constraint on your problem, and you can create a problem statement which can be explained through Pauli XYZ operators, XYZ gates. It's as simple as that. And if you create a problem like that, and the problem solution will lie on the ground state of that particular Hamiltonian, like a series of XYZ gates. So this is like if you can use this, so if the VQ is efficiently implemented, then we can say that we can find problems to many real life problems also. We will be focusing on the expectation value, which is the average over some state. So this expectation value, like if we have some observable or an operator, like here O is the operator, and there is some state psi, then the expectation value is given by the average of this operator is given by over psi is simply is this, like and this O, like as I told you that this O should be like in such a way, this O is defined in such a way, like in our problems, like real life problems, this O is the Hamiltonian of the problem, like the problem statement itself. And this O should be implemented in such a way that we will be able to find this expectation value. Like we need to piecewise like find that what is the decomposition of O, and how the expectation value of each of the parameters constructed O is giving. So so this O has a particular construction, and if we can find this construction, then we can say, okay, we can find the expectation value of it. And as you can see that this is the this is actually the way to this is actually one of the ways to write this O, this observable. And if we can efficiently write this O in such a way, like the summation of some many O, like many operators, and this Wi is like called the weight, like this operator has this weight, this operator has that weight. And if we can write some Hamiltonian in such a way, then you can say, okay, we can find an expectation value of it. So
Akash,
actually,
just a question. In the previous OI, do they need to be local, or do they? I mean,
yeah, actually, this O is like the problem statement or the Hamiltonian of the full system, and this OI is like how these operators are locally operating. Like in the first qubit, like if you have a 4 qubit system like O, and then this OI may be interaction in the first qubit and second qubit. And so this is like that. So you're right. This is giving understanding of how the system is locally operating.
Yeah. So then it may be, yeah. So then that's why it's also easy to that's what makes it easier to compute.
Yes,
right?
that is also true. Like you put up a very nice point. Like if we can find the expectation value locally, then the global assumption will be like proper.
Yeah. Yeah.
So
thanks. Yeah.
Okay, thank you very much. And so this is one of the examples. Like I told you, this sigma i's and sigma j's are like Pauli operators. And as you can see, this tensor product is like defines by this omega, this sigma I is applying on ith qubit, this sigma j is on jth qubit, and maybe there are some sigma k, sigma l, sigma m, like mth qubit, nth qubit, or some like it depends upon the dimension of the system. And so if we have some real value parameters like beta, then we can prepare a quantum state psi beta, which gives the expectation value in such a way. Like as you can see that, and these betas are the actually the answers which I was talking about, the parameter of the particular answers. And if we found the expectation value, then it is actually lower bounded by the lowest eigenvalue. And I'm going to discuss this proof of that. Like it doesn't came from the sky, like it has a like small proof and very constructive proof. I'm going to discuss about that later, not in the slides. So as you can see that this expectation value is greater than equal to the lowest eigenvalue. So that means if you can minimize this expectation value, that means that is equal to, that is the equal to sign, right? Because this is the minimization, like, or else it is maximum. So what happens that you find the lowest eigenvalue. That means you can say, okay, this expectation value actually is the cost function. So that is the answer to Aditya's question, that the expectation value in the VQE problem is itself a cost function. And if we can minimize this expectation value, then what happens that we find the ground state or ground state, and at the same time ground eigenvalue. So so this is the steps of the algorithm. Like we discussed everything explicitly, and now we are going to compile everything. Like we basically prepare a state psi b, and this preparation of this state is like think about it like like a Hamiltonian, and you are going to find the expectation value of some of the Hamiltonian, right? And then what happens that you don't know that which state the Hamiltonian is corresponds to. So you try to create a state, like a trial state. So this psi b is actually a trial state, and this rho b is the density operator. And Kate and Bra, like formalism, you can easily create it. And this beta is the parameters. And basically, we found the expectation value, as I mentioned, of H, like the Hamiltonian of a problem. And this is like, and we use, okay, there is a sign missing here. And this we use the like an optimizer, classical optimizer, to evaluate this, like to minimize this particular entity, like a cost function. And if we can found, if we cannot found this minimization, then we do some iterations on the particular beta. Iteration means that we change the betas, like the value of betas, like the array of betas or a list of parameters, and we run this algorithm once again. So as you can see that this is the better illustration of the algorithm. So we're starting from 0, 0, 0, and we are preparing the trial state because we don't know that which state this particular Hamiltonian, like for which state it is going to give us the lowest, like the cost function will be lowest, right? So we are initiating without any guess at this particular point. And when and we are measuring the output, and from the measurement we mean that we are basically finding the output state after this unitary operation, and then we are finding this expectation value. Now the expectation value is nothing but the trace of the multiplication of the output density matrix and H. So because at the output we are going to get some state, like the state vector or an array of vectors. And what happens that if we get that array, then we can create a density matrix from it. And if we can create a density matrix, then we can multiply with the Hamiltonian we have, and then we can find the trace of it. So if we find the trace of it, then we can minimize that particular value using classical computation. And if we don't find the minimize, like if the output is not close to 0, then we can update this beta and run this once again. So this is a very simple illustration.
So,
And
Akash, there's a question, like, can you re-explain what the cost function actually measures? Like, it is not the time, right? It's measuring how the actual expectation value of the energy, but maybe people are not very familiar with the expectation, what expectation is. So
yeah, so expectation value is actually like if we have any operator, like it doesn't matter A, B, C, D, then if you have a quantum state, then the expectation value is like this state, like complex conjugate of that state and this operator, like because they're all matrices, right? Like this is an array, like a column matrix, this is a row matrix or something like that. Then you can create anything. Like, do not consider it as a quantum system, just consider it as a matrix. So you have, this is like a row matrix, because this psi b is a column matrix, like a column of vectors like that. And if we have the complex conjugate, this will be psi b, and you multiply it with this particular operator, which is also a matrix. Because
okay. So, but maybe that's a wrong interpretation. Like, what he wanted to know is what is actually being minimized. Like, what is the cost function?
Okay, the cost function is actually the energy.
Yeah, so basically, whatever optimization problem you have mapped it onto a Hamiltonian, and a Hamiltonian is basically an operator to calculate the energy. So when you find, and with
yes,
this,
so actually,
with this cost function,
once again.
So I was just saying, with this cost function, you're calculating the energy and you're trying to minimize the energy.
Yes,
so
that is the basic idea.
Yeah, great.
So the minimization of energy is the output energy is the cost function. Yes, and we are trying to minimizing the energy.
Yeah, great. Thanks.
Yeah, no issue. Thank you. And so this is the algorithm, and actually, as you can see that this answers, I didn't define a particular like format of these answers. And what happens is that these answers can be combination of any gates, like single qubit gate or 2 qubit gate. So, but there are no golden rule for creating the designs of these answers. Like, you can create any set of gates, like any length or any short length of big length circuit, big depth circuit. It depends upon you. And also, not all states can be efficiently prepared. Some state can be approximated, because I told you, like in our current system, all the qubits may be not connected. So what happens if we are constructing if you are having a state in mind, and you know that which gate you need to connect, then maybe some qubits are not connected. So you are not getting the state which you are expecting. So these answers sometimes may not be perfectly described through your gates. And actually, there are two famous ways to define these answers, like just a abstract like a abstract design. It is called UCC. It is like unitary couple clustered and qubit couple clustered. I mean, you don't have to think about it, but we will not go deep inside this. But there is a very efficient way, which is like easy to understand. Is like hardware efficient answers. And this is like if you have a 000 state, we are basically applying rotation to each qubit, like 000. So this 000 is rotating to some certain state, and then we are applying these entangle gates, like control naught or control Z, to each and every qubit to connect all the qubits to create some entanglement on the state. So what happens? It has been observed by the authors here. It has been published in 2017 that if we can create entanglement between all the qubits, then the outputs, then the cost function becomes easy to minimize. So that is the main purpose, because that's why it is very hardware efficient. We don't need a very depth circuit or too many gates. but we can get a well approximate of the cost function. Like we can minimize the energy very fast. And there is a very technical discussion about this, like UCC answers. I think it is better to like skip this for now, because it is basically that how this UCC answers is defined. Like there are some fermionic excitation operator. Like this UCC answers is all about like to excite the input state to some other state, and this TBs, like this T are the operators, and they are like some fermionic operator. Like fermion means you can consider some electronic operator, like an operator consider particularly to excite an electron, like an input state, because we're considering Pauli operators, right? And so this construction, particular construction, is very abstract, right? This is very mathematical. So we need to map this particular construction into native gates. And there is a very well-defined method which is called totalization. And I will discuss this totalization in more details like after this discussion. And this totalization is like dividing the whole unitary operation into different parts. Like you like consider that you have an unitary operation and that works for maybe 1 second. Like after 1 second, you're getting the output, right? So you are dividing the big answers which work for 1 second into like 1 millisecond. Like, okay, I have an unitary which will work on 1 millisecond, 1 millisecond, 1 millisecond in particular time intervals. And actually the main idea of doing like constructing this particular, like dividing this unitary, is to find out that which gate can be implemented to evaluate this, to do the evolution of the circuit for that particular 1 millisecond or some particular small time. So this is like this totalization is just dividing the big unitary into very small unitaries.
So Akash, there was a question like, so does every problem need its own ansatz?
Yes, like, okay, so yes and also no. That's a very big thing. Like creating an ansatz depend upon firstly understanding how you perfectly understand the problem and also your observation. Like think about, you consider some particular gates like rotating X gate or rotating Z gate, and you're getting some output. And you are trying to minimize that output, like the energy, and you're trying to minimize the energy particularly. Okay, so you got something like 0.01, but actually it is not close to 0, right? So next time you thought that, okay, let me remove this X gate, and in place of X gate, let me use some Y gate. And when you use the Y gate construction, then you found some energy like 0.0001, which is less than the previous energy you're getting. So you can say, okay, this ansatz is better. So it is like it is depends upon how many like trials of the experiment. Like
so it's very heuristic. You mean that you have to?
Yeah. This is like you have to use some kind of brute force to do that. Like I mean, there is not a shortcut way to define the answers. So
right. Yeah. Thanks.
Yeah, no issue. So yeah.
But maybe we can leave these.
Yeah. So I'm going to leave this.
Yeah.
And I'm going to also discuss this later. So okay. So let me show you some examples, right? Like I was talking about VQE and this stuff. So how does actually it looks like in Qiskit? Because I implemented everything is Qiskit. And as you can see that these S's are spin operators. And these are like this half of Pauli X, Pauli Y, and Pauli Z operators. And this is like interaction of two spins. As you can see that two spins are interacting. And if we put this, and this is like simple dot product. It is not a vector product, it is a dot product. And if you implement this here, you will get an Hamiltonian, like where two spins will be connected. Like this circuit, like first qubit and second qubit will be interacting, second and third qubit will be interacting, third and fourth. And actually, two spins means you need double qubits, because we have half and like spin up and spin down. So to define that, per spin needs 2 qubits. So that's why you need total of 4 qubits to implement the circuit. And now, if you plot that particular energy with number of iterations, then what happens that, as you can see that I plotted for SL, SQP, Copeland, Nelson, Mead, and these three are actually classical optimization methods. If you search about them like SciPy optimize, there is a very nice function defined by Python, defined in the Python language. I use Python actually, and if you can search about them, then you can find. And I just like did a comparison that which method can give us better approximation of the energy. And as you can see that when we are using like my construction was basically like this, like we have 0 0 0, and I did like apply rotating Y gates in each qubit, and all the qubits are next connected with control rotated X gate in this, and here control rotated Y, and I will show control rotated Z and control Z also. So my main point is that how to find a good answers. That is the question, right? That is someone asked just before. So how to find these good answers and how to find good optimization method, because there are like 20 optimization methods maybe available, maybe more than that or less than that. I mean, I'm just saying a number, like a very huge number. So how to find good like a good answers and also good optimization method. So it is better to see, right? It is better to observe. So as you can see that if we use like nail-the-meat is just finished here, like it didn't go for like more iterations, and it looks like that it is saturating here. I mean, it will go for like more iterations. Like more iteration means like more time consuming, and we don't want too much iterations actually. Like if we want to run an algorithm very fast, quantum algorithm. So as you can see that this SLSQP and Kobla, these two methods, like classical methods, are very nicely like giving us -2. Actually, the ground state is -2 in this particular Hamiltonian construction. And so if I ask you that which method you are going to use, like between these three, you must be saying that I'm going to use SLSQP because this is converging very fast to the -2. And like you can also use Kobla, I mean, if you are like interested, but it is taking a lot of time to converge. But at the same time, if I tell you that which circuit you are going to use, circuit with CRX or CRY, you must say I should use CRY, right? Because see, this is converging at 250 and this is converging at 500. So I mean, I don't want too much iteration because it will take a lot of time and it will take a lot of resource. Like time means electricity bill, come on, like we don't want to spend a lot of money, right? So CRY as entangular is giving us the expected result we want, like the minimized result, with less iterations, less time, less money, and everything less. Like all the resources are less. So between these two gates, I will use CRY, and between these two methods, if I use CRY, then I will use Kobla, not SLSQP, right? Now, move more. Okay. Now we are comparing between control rotated Z gate as entangular and control Z gate. Now, as you can see that the comparison is very much nice, because at this point, as you can see that both are converging in reasonable amount of iterations, or you can consider it as evaluation time. Like forget about the iteration time, like or evaluation time. And as you can see that this is converging almost around 500 iterations, but this in this case it is converging around 200 iterations. So I will say that between control rotated Z and control Z, I will use control Z, that is better. But I will use SLSQP. So in this particular method, you should use entangular as control Z, and as a classical optimizer, you should use SLSQP. So as you can see that we can define a particular answers and a particular classical optimizer depending upon our observation. So this is all about how much time you spend in a particular problem and how many possible observations you are doing on that particular problem statement. So this is the thing. And I have another example.
Just one question is, are these all equivalent? Like the output that you get or the problem that you're trying to solve using the CRZ, CRX, CRY, is it all the same problem?
All the same problem, because as you can see, all the converging -2.
Okay.
Same Hamiltonian, same problem.
Okay. It's just different answers that you're trying out and you're seeing which is better.
Yeah. So as you can see that this is a very nice example of how to choose an answers and how to choose a classical optimizer.
Right, thanks.
Yeah, no issue. So as you can see that I considered a Heisenberg model. Actually, I hope you, some of you may know that there are some problems like Ising models, and what they use only the Z gates, and they are just like very simple form of Heisenberg model. So here I give you, like present you a more mature model, which is called Heisenberg model, depend upon all the components of the Pauli matrix, and as well as you can converge it into like an Ising model, like by discarding X and Y. And this is what I showed in the next like this. And as you can see, it is converging to -1 as we expect. And the conversion rate is very low. But as we discussed, the biggest problem, like the more mature problem in this case, so I'm going to not discuss about this here, but you can always go through the slides and ask me the questions and see this. Like in this case, like when we are considering only Z gates, not XY, like we are getting like with less than like 100 iterations. And I don't know which optimizer to choose here, like Copeland, SLSQP, but you can choose any one of your choice. And of course, use Control Z as an integral, because or else you have to go through like 200 or 250 iterations. And thank you so much for your attention.